Hello everyone, welcome to another episode together. In today's episode, yet another two more new topics, superposition as well as standing waves. For some of these, you'll have to set up your house in a way to try to simulate it so that you can witness it, because unfortunately, with this medium over here, I can't repeat the same results this way. Okay, but just to let you know that all my recordings, they are available in the Google Classroom, so you can download the MP3, play it for yourself, and witness the crazy outcome of it all. A few things just to talk about first, and this is just more of a review. First off, here's an example of a single sine wave that's transmitted on a rope. It's like those thunder ropes where you just simply whip it up and you let it ride. And you can imagine the wave looking just like that. And that is a result of just transmitting a single sine wave through a rope as a transverse wave. That's what it's going to look like. Okay. Now, what if you end up doing it where you just keep on going up and down continuously? Well, then you'll have a sine wave that propagates across. And that is the nature of transverse waves. The energy disturbance is up and down, but the wave travels all the way across. Okay? Now, as it travels across, as long as it's through the same medium, it'll just travel in that direction forever and ever and ever. However, if it changes mediums and there's an abrupt change, then you'll have a partial reflection, concept that we covered 2 classes ago. Okay? So if you go from more dense to absolutely nothing at all, it will result in a positive reflection. I think that's the next slide. Oh, it's afterwards. Anyways, I'll just summarize this right now, okay? Because yeah, you have to deal with these reflections on the far end, okay? So if you go from one medium to a different medium, you're either going to result in a positive reflection or a negative reflection. However, if the mediums are the same before and after, the wave will just keep on traveling indefinitely. That we need to keep in mind for the next slide, okay? So as long as you're with the same medium, like in this picture over here, okay? Here is a material and here is another material. As long as they're exactly the same piece of material, this is all the observer will see at the end. The wave will just keep on traveling through. You're not going to see any sort of reflection. Now, what you can also do is that instead of transmitting waves from one side all the way across, you can end up having some sort of war between 2 separate waves, and you have them coming towards each other. Like in this example here. Unfortunately, this isn't properly color-coded. It looks like they're just simply bumping off each other, but they aren't. Okay, so these waves are not just simply colliding and bumping off each other. In fact, what's really happening is that the wave that was traveling towards the right at the beginning of this animation, right here, all it's doing is that it's mathematically reacting with the other one, but after the fact, that wave is still traveling across. Okay, so that has not changed. That wave that was traveling towards the right, it's still moving towards the right afterwards. And the same is also true with regards to the wave that's coming in from the left, if this would animate, okay? So the wave going towards the left right now, after the collision, it's still traveling towards the left as if nothing happened at all. And that's what superposition is. It's just the interaction of waves where there is no cancellation of energy. What you will see is that it's a mathematical sum of the two when they are on top of each other. So if you look at this setup right here, you'll see that they're both at an amplitude of 1. And as you may know, 1 plus 1 will give you 2. So when they're directly on top of each other, they end up forming something known as a supercrest. Okay, so the highest peak is known as a supercrest. I'm missing out on my animation, but you can imagine that if I had 2 troughs coming together, the moment they're on top of each other, they form something known as a super trough. And if you have a base interacting with another base and they come together, what do you get? You get a Nicki Minaj. Don't know how many of you guys get that joke. Okay, so this is the occurrence, this is the outcome of what happens when you have a trough interacting with another trough, or a crest interacting with another crest. Okay, but what if they're out of phase? So you have a crest interacting with another trough and they come together. What will it look like once they're on top of each other? Okay, here's the animation as it starts, and X marks the spot. Boom, they disappear, and then they reappear again. Okay, as I said, the energy of the wave, the proper term is the momentum. Okay, the momentum of the wave does not disappear. So I'll just let the animation start all over again just to emphasize what I'm talking about. The momentum of this wave over here as it's traveling towards the right, it doesn't disappear at the middle. You can see that it still keeps on traveling towards the right. Similarly, the inverted wave that's traveling towards the left, even though they may temporarily go to 0 right here, it'll keep on traveling towards the left. All you're observing is just the mathematical interaction of these two. So anytime you have a +1 interacting with a -1, then yes, to the visual eye, you're going to see that they'll cancel out. But that's just the mathematical outcome there. The energy is still there. So in other words, the natural movement of the wave is still traveling across. It's just that at that snapshot on time, you suddenly see a 0. And when you suddenly see that 0, it's known as a node. All right. So that point X describes something called a node. I'll give you guys a moment to jot this down. Again, with regards to the animations, I've already provided them in the Google Classroom if you need to watch it again. As for copying it down, there is no easy way of drawing it down other than just drawing just a dot showing that this is the result of the wave on top. And the next one, you'll just see a dot where the dot represents the node. Okay, so at best, this is all you could do in your notes with a static image. Anyone else still need a bit more time before I move on to the next topic? Okay, I'll wait for the hands to go down, and then I'll advance forwards. Okay, now that everyone's hand is down, we can advance on. Okay, so for this first part over here, we're just seeing what the simulated outcome will be once these two waves interact with each other. If you already printed out your course pack, I believe there's a picture of this in your course pack. I think. No, there isn't. Never mind. There isn't. Okay, so we're just trying to see, what is the outcome with these two waves interacting with each other. So we have a rectangle traveling towards the right, and we have a upside down M traveling towards the left. Okay, and the question is, what does it look like when the waves are directly on top of each other? All right, to help guide us into the answer, what you would want to do is that you want to draw these two waves as a dotted line on your paper. Okay, so here's a dotted line representing the rectangular wave, and I guess I'll use a different color for the upside down M. And by drawing this template out in your notes, this helps you figure out what the mathematical sum is at every single point. One thing that's true is that 0 plus 0 will always give you 0. So you can see that the leads and the tails of both of these, since they're at 0, these two regions here will definitely be at 0. Okay, so 0 plus 0 will definitely give us 0. So we know that there'll just be two horizontal lines riding right at the rest, and that's it. Okay, now let's analyze section by section, piece by piece, what the mathematical sum will be. If you look at the rectangular wave, which I'll call the red wave from now on, it initially has a value of +2 units. As for the upside down M, which I'll call the blue wave from now on, it has a value of -2 units. And as you know, 2 plus -2 will give us 0. So we know that at that point over there, the value will temporarily be at 0 right there. Again, the waves are continuously moving, and this is just a picture or snapshot of what it will look like at this point in time. All right, so at that stage in time, it will be a rest there. And we can scan through the entire picture to have a glimmer of what the rest of the wave will look like when they're on top of each other. Okay, I guess the easiest points to look at is to look at the grid marks. Okay, so for this grid location over here, you can see that the red wave has a value of +2, and the blue wave has a value of -1. And 2 plus -1 gives you +1. So you know at that point, the value will be denoted by that blue dot that I've drawn over there. Okay, I'm going to analyze this part on the grid as well. At this portion of the grid, you'll see that the red wave has a value of +2, and the blue wave has a value of 0. And as you know, 2 plus 0 will give you 2. Next, we're going to take a peek at this grid line right over here. You'll see that the red wave has a value of +2. The blue wave has a value of -1. So 2 plus -1 will give you +1. Lastly, when we take a look at the grid line right over here, at this point in space, we see that the red wave has a value of +2, the blue wave has a value of -2, and 2 plus -2 will give you 0. I'll just maintain the same color consistency. Why not? Okay. So just let the blue line that I'm drawing here, just because I'm using this color, represent our final answer. Okay. But you got to keep in mind that these waves over here, they're not discrete. In other words, they're not just drawn in one point in space and time. It's a continuous line. It's a continuous wave. In other words, there are still values in between the grid lines. They do exist. So let's take a look at them right now. Okay. So I'm going to look at the point in space between these two grid lines over here. If you look at the red wave, it has a value of +2. And if you look at the blue wave, it has a value of -1.5. So 2 plus -1.5 will give you 0.5. Sure, I'll go over here as well, okay? Right here, the value is +2 for the red wave, and for the blue wave, it's at -0.5. So 2 plus 0.5 negative will give you 1.5. And you don't necessarily just have to cut it in half. You can cut the half in half again to find out another point over here. Okay, so now we're splitting it down into quarters right now. Okay, so at this quarter point over here, you see that the red wave has a value of +2. The blue wave has a value of -1.75. And 2 plus -1.75 gives you 0.25. And you can keep on going through this exercise, right? You can split it up in half again, split up in half again, and just keep on going at it. And after doing it, you'll notice that the trend will look more or less like this. All right, so when it comes to test time, do you really have to go and split it all off like that? No, you probably don't have to. The moment that you see the trend that exists, you probably could just connect the dots, and trust that that will be the outcome. In fact, that will be the case. Anytime that you add a linear relationship with another linear relationship, your final answer will also be linear. Okay, so on the left-hand side, I'm just showing you the logic of what's going on. And on the right-hand side, if you just need to choose two extremes and then figure out everything in between, you can do that as well. Was there a hand that was raised up? Or did I just answer away that question? Oh, hand is still up. Yes.
Oh, sorry, I'm a bit confused where you're getting your values from. Like,
okay,
can you just explain that again?
How about I just explain all of it one more time?
Thank you.
Okay. So I'm going to represent the wave on top as the red wave and the wave down below as the blue wave, and I'll let the color green be my answer. Okay. So that's what I have down here. It's just when the red wave is directly on top of the blue wave. It doesn't have to exactly be down there, but I'm just using that as one example. Remember, they're moving in real time. So in other words, a wave over here will be different than the wave over here, which will be different than the wave here, which will be different than the wave over here. Okay, so it's never going to be the same wave twice. But we're just curious on what they look like at one moment in time. And I just decided to say, hey, what if they're on top of each other like so? What will the corresponding wave look like? And we have to keep in mind that the answer is going to be the superposition of the two waves. In other words, it's just going to be the mathematical sum of the two. All right. The waves won't disappear. It's just this is what we observe at that moment in time. It's very similar to these animations back here, right? You can see that the waves, they don't disappear. Okay, they don't disappear. Instead, all you're seeing is just the real-time update of what their numbers are currently at that moment. That's all it is. So in other words, a +1 plus -1, if they're on top of each other, it's going to go to 0. And if it's +1 plus another 1, then yes, mathematically, it'll add up to the value of 2. Now, this is an animation. And animation outcomes will be different than static images. And that's all this is. This is a static image rendition of it, except that we're not using those clean waves. We're using these ugly looking things so that I can get a more complicated idea across. Okay, so now let's try to figure out the sum of these two waves and what the picture will look like. And really, all we're doing is that we're just taking slices in time and in space, or just space, because time is frozen right here. So we're taking a look at slices in space and seeing what the mathematical sum is at each of these points over here. Okay, pretty much all the points across. Now, for the points on the left-hand side, just to save ourselves a lot of time and effort, we already know that 0 plus 0 equals 0. Yeah, I'll stick with black. Black will probably render better. Okay, so these two edges over here, or ends, they'll just simply be horizontal lines because the 0 from the red wave plus the 0 from the blue wave will equal 0. Nothing special there so far. The interesting stuff happens in this region here. So that's why I'm going to take small little time slices and see what happens. Usually you just want to take a look at what happens at a vertice and go from there. Okay. So at this point over here, you can see that the red wave has a value of +2, and the blue wave has a value of -2. +2 plus -2 will give us a value of 0. I'm going to erase the black line for now just so that we can clearly see that I've drawn a dot there to tell you that it's at 0 at that point. Next, I'm just going to move on to the next grid line, so just another point in space, and just analyze what the numbers are. So here we see that the red has a value of +2, and the blue has a value of -1. 2 plus -1 will give us a value of just 1. So there's our next marking. Next, I'll take a look right over here, and we can see that the red wave has a value of +2, the blue wave has a value of 0. 2 plus 0 will give us just 2. So far, so good? Okay.
Yeah.
I hope that part makes sense so far. In fact, we can pretty much solve the left-hand side right now. We know that it's going to be a horizontal line on the left, and because of the relationship that we see over here, there's a good chance that this is all that's being created. Are you okay with that?
Yeah. Thank you.
Yeah. And again, if you're not okay with it, then yeah, you could just keep on breaking it down into smaller pieces if you want to. Okay. As I said, usually what you do is you look at the vertices of the graphs, and that's probably the good extremes to guesstimate what the outcome is. Okay. But on the right-hand side, sure, I'll do it the long-winded way. Okay. I'm going to take a look at it at every quarter sample. So I'll sample it right here, then I'll sample it the next quarter, sample it the next quarter, and I'll just keep on going until we get to the end. It's a much longer way of solving it. If you want to do it that way, you're more than welcome to. Okay. So at this point over here, we have 2 plus 0. 2 plus 0 gives us 2, so we know that point right up there. We're aware of that point. Next, I'll just go a quarter of a slice through right over here. And now we're analyzing 2 plus -0.25. So 2 plus -0.25 will give us 1.75. So at that point over there, the intensity of the wave will be at 1.75 units in amplitude. Erase it again, analyze it right here. Okay, now we have a value of 2 plus -0.5. 2 plus -0.5 will give us 1.5. Repeat it again right over here. We have a value of 2, and over here it's -0.75. So 2 plus -0.75 will give us 1.25. All right. I hope that with that you get the gist of what's going on. Okay, I'll just do one more. Right over here, we have a value of 2 plus -1. And 2 plus -1 will give us 2. All right. And you can keep on doing that trend all the way across. And again, there's no shame in doing points even in between it. But you'll see that by the time you sit down and do all that math, half an hour has gone by. Meanwhile, a question like this, you should be able to answer it, within 5 minutes. So that's why you're going to look at the extremes. And by looking at the extremes, you can estimate what the corresponding wave will look like. Okay, so that's how you would solve these problems here. Now, one more slide just to show you afterwards, and you'll just have in your notes just to remind yourself that the red wave did not disappear. Okay, the red wave kept on traveling towards the right. So a few seconds after, the red wave will be all the way over there, and the blue wave will now be on the left-hand side. All right, so if you want to jot that down, you can. It's just to point out that these two waves, they just superimpose on top of each other. You're just seeing the temporary answer at that point in space and in time. That's all you're observing. There you go. Any other questions before we move on? Oh, sorry, I didn't realize there were text questions. I was on the wrong slide. Okay, so there's a few questions here. Never mind, I got it. That's good. So the black line is a superimposed pulse. Yeah, it's the resulting wave. How about that? It's the resulting wave that you see. So it is a superimposed image. Remember, this is all happening in real time. So at every split second, the picture will look slightly different. So if you take a look at your homework, question number 2, I think that's a better question to do for homework. Okay. Question number 1, you could go through it. The problem with question number 1 is that it's not being very specific. So you're not going to get a specific answer. Number 2, it's discrete. It's getting to the point that, 1 second has gone by. It's traveled at this distance. So exactly at this point in time, if you just take a picture, what would it look like? All right. So a better question to work for homework is question number 2. That would be a better question for homework. Any other questions before we move on? Yep. Course by page 65, number 2 is a better question. You could do number 1 just so that you have a subjective answer, but it's not going to be absolute. Okay, because again, it's dependent upon the artist's drawing. Remember that because these questions over here have picture answers, I can't exactly give you a picture answer down here. There's no space for it. So if you go into your Google Classroom and you look at the top with the answer key, that's why that answer key exists. It's for the homework questions where you have to fill in the blanks to get to the answer. Okay, so for the visual answers, you'll see the answer key over there. So just remember that in tonight's homework. Once you're done with it, go into Google Classroom, take a look at the answer key, or look at the attached file on this video at the end, and then yeah, you'll be able to see what the picture should look like once you're done with it. Okay, and I think that's it for superposition. Oh, I kind of jumped ahead. I talked about this part over here. So let me just talk about it one more time. Okay. Sorry, the audio recordings, I thought it was in this video. I have a feeling it's the next video where the audio recordings are. Okay. So you can listen to the audio recordings for tomorrow. Okay. So here are the 2 outcomes of waves when they interact at a boundary. The first type of boundary is one where it's a brick wall. Okay. So the wave travels all the way across, whacks against a brick wall, bounces off, and reflects upside down. This is a case where you're going from more dense to pretty much no density at all, or the hardest object. Okay, so infinite density. You can think about it as an infinitely dense object. Okay, so when you reach an infinitely dense object like a brick wall, the wave will always flip upside down. If you don't believe me, take a skipping rope, tie it against the doorknob in your bedroom. When you whip the wave to the left, you'll see that it'll ricochet and bounce off the other way and return back to you the opposite way. Okay, so that's an experiment you can try out at home. Tie a rope against a rigid object like a doorknob, whip the rope one way, and you'll see it will reflect the opposite way in return. This has also been simulated in that animation that I showed you guys yesterday. Okay, this is the same outcome. The other weird one, which it's harder to simulate at home, what you would do is that you get a skipping rope, you tie a little circle on one far end. Then you find a broomstick and you attach it through the loop of the broomstick so that your setup looks kind of like this. Okay, so this is a case where you go from a medium to nothing at all, just space, all right, to a vacuum. Anytime that you go from a medium to a space, you end up having this type of reflection. Okay, you end up getting a positive reflection instead of an inverted reflection. Again, if you're trying to copy this in your notes, what you'll do is you'll draw a before and after. So your before would probably look like this. And your after would look like this. Now, if you're wondering how would you differentiate between the 2 pictures, I haven't explained this explicitly yet, so I'll mention it right now. To describe to a reader that you have a fixed end, you'll draw a circle, a black dark circle. You can see that I did that here. The black dark circle tells you that, yes, a node will be formed there and it's a fixed end. Okay, so that's how you draw the first one in your notes. As for the second one, what you'll draw is that you'll draw this loop, V. Afterwards, it'll look identical when it returns back, but V will be in the opposite direction. Okay, so that's how you draw in your notes. Again, a dark circle for fixed end reflection, a loop to indicate that it's freely able to go up and down. Now, one thing that will not render in your notes, but this is something that's interesting that does happen, is that anytime you have an open end reflection or a free end reflection, remember it came in as 1. When it reflects back, because it's still upright, it'll return as 1. And as you may know, 1 plus 1 equals 2. So let's see that happen. There's 1, and there you can have it. 1 plus 1 equals 2. All right, so that's something that will be missing in your notes because you can't take that snapshot right over there. I mean, if you want to draw a midway picture, you're more than welcome to. Okay, picture midway between the two, where in the first case over there, it's a node. So if you look at what happens when you reach there, it looks flat. There you go. See, it looks flat right there because the wave has canceled itself out mathematically. Is it really gone? No, the momentum of the wave is still there, but because it returned back negative, a positive 1 plus negative 1 temporarily gives you 0, and that's why midway through, it just looks like a flat line. Take a look at it. Flat line, inverted. Okay. So that's all we're seeing. We are seeing the superposition of the two waves. One as a fixed reflection where it inverts, and then the second one as a open-end reflection or free-end reflection where it remains the same way backwards. And 1 plus 1 will temporarily give you a value of 2. And that's why the amplitude temporarily amplifies. In fact, that is one of those weird life hacks that is done in industry. If you find out that the wave is too weak, but you still want to measure it, what you'll do is that you'll set it up so that you go in the setup. Okay, so you're going through a medium to something that has no refractive index or it's open space. Okay, so you go from a medium to open space, and temporarily the value will double so that you can still register and read that very weak signal. The consequence of it is that, yes, it will reflect back. All right, and the assumption is that if it's a weak signal, that's no big deal. It's going to dissipate and be 0 on the far end. Otherwise, if it does return back as an open wave, it may destroy your transmitter. Can I explain the circles one more time? Certainly. Remember that when it's a solid circle, it represents a fixed end reflection. That's how you denote it. When you want to talk about a free end reflection, also known as an open end reflection, sorry, I do use these words interchangeably. Okay, an open-end reflection, to represent it, you'll draw a circle, indicating that it's freely able to move. Okay, I hope that answers your question there. Okay, and just to better reinforce all the stuff over here, we'll go back to that simulation that we dealt with earlier. I really like the simulation because it is an accurate rendition of how waves behave. Again, anything that behaves as a wave will abide by this crazy simulation here. So this first setup over here is that of a fixed end reflection. All right, you can tell because this is a rigid object. That's why they use the C-clamp. They could have drawn a wall instead. When it transmits a positive wave, it returns back inverted. And with regards to the C-clamp over here, because it's rigid, it's heavy, it has a lot of mass, it usually ends up reflecting the wave as well, like so. In an ideal system where there's no internal resistance or no damping, this wave will happen forever. But the reality is that there's usually internal friction in the medium itself, and you lose some of that energy. Okay. Nevertheless, this is a good rendition of what happens in a fixed end reflection. Now, if you have an open end reflection, you can see that there's a circle that's drawn over here. Whenever I transmit a wave, doesn't that look exactly the same as our previous circumstance? Okay, positive returns back positive. If it's inverted, it returns back negative. Another important thing is that right at that junction point, you'll see that the amplitudes do temporarily double up. In other words, the energy has been amplified. And if this was sound, the sound is amplified. Hopefully you understand that reference in our next day's lesson. Okay, because that is the truth of what happens when you go from a medium to an open end reflection. You get this artificial amplification. And lastly, I'll just run it right now since we're in the simulation over here. If the mediums are matched up, that means it's as if you have this wire that goes on and on forever. And in that case, there is no reflection. Again, when the mediums are matched up, in other words, the refractive index of this cable over here matches up with the refractive index on the far end, then the wave will just transmit one way and there's no reflection in return. Remember that electricity also behaves as a wave, except that for cables, it's known as impedance. So as long as the impedance of the line is the same on both sides, you can transmit your signal, whatever it is, the telephone call, and you're not going to get that weird echo afterwards. As I mentioned, anything that behaves as a wave will definitely abide by this, and that's why I love this simulation so much, because it is an accurate rendition of it. Okay, and just a little bit of a review from last day's lesson, because I do want to talk about partial reflections, and you'll see that this partial reflection still abides by what we talked about before. Okay, so when you go from less dense to more dense, you're not at a brick wall yet. You're at a partial brick wall. So you will have this inverted reflection, as you can see here. This slide over here, no, you don't need to copy down because you've already copied it down. But I just want to reinforce the knowledge that was covered yesterday. Okay, so when you go from less to more, you will have this partial reflection, but you will also have a definite transmission as well, but the wave will travel a lot slower. When you go from less to more, yes, the new wave will travel a lot slower. What is dampening on a car? It's the suspension on the car to prevent the car from shaking up and down afterwards indefinitely. Because if it did that, a lot more people will be throwing up on their ride. Okay, so I'm just playing these videos just to remind you once again that the outcome is still true. Okay, when you go from less to more, you're going to have an inversion in the reflection. And when you go from more dense, less dense, you'll see that the reflection returns back positive. Okay, that is the nature whenever you go from one medium to the next. Any questions so far before I advance on? Okay, just so that we have in our notes, let's just talk about these grade 9 and grade 10 topics. You had a question beforehand? What's up? No question. Okay, next slide. Do you need to copy it down? No, it's just terminology. Okay, what exactly is refraction? Again, refraction is an outcome when you change from one medium to the next and you're not traveling along the normal. For example, in a picture that looks like this. As I'm not traveling along the normal, where if you recall, the normal is a line that's perpendicular to a plane. Same line, same definition that we used back in grade 10, right? The normal. Okay, so here's the incident wave. And when we go from less to more, the wave will bend closer and closer towards the normal. So this is just a brief review of grade 10. Okay, you have your theta I, angle of incidence, and you have your theta R, your angle of refraction. So refraction is just the reality of what happens when you travel from medium A to B at an angle, at a non-zero angle to the normal. This will always happen. And you can imagine if you go the other way around, then yes, you will refract away from the normal. Don't worry, you're not going to be tested on grade 10 knowledge. I'm just telling you that this is the definition of what refraction is. And it's different than the definition of diffraction. Diffraction is a reality that anytime you have a wave and the wave moves through an opening, it will cause the wave to bubble out, like so. Okay, so you have an incident wave and it goes through an opening or an edge of a wall, and the waves will end up bubbling out. That's diffraction. So we're just keeping this just as terminology for grade 11. These two concepts will be covered in more detail in grade 12. Any questions before we move on? Okay, so if you already know the definition of refraction, then you don't need to copy it down. And now you understand what diffraction is. Okay, again, if you want to copy this down afterwards, you're more than welcome to. I just don't want to spend too much time on this slide here. It's just terminology. Okay, instead, this is where the more important meat, I guess, comes in. Okay, what exactly is a standing wave? And we've witnessed a standing wave when we were doing our simulation from last day. I think I closed the window already. That's okay. All right. So what's happening with a standing wave is that you're transmitting a wave all the way across, and then when it reaches a junction point, the wave reflects backwards. But as it reflects backwards, you end up having this illusion where the wave doesn't seem to be moving at all, right? It just seems to be like a wave that's standing still. It's vibrating, but it's not moving to the left or moving to the right. Truth is, you're looking at the superposition of these two waves. You're seeing this incident sine wave moving towards the right. It didn't show it here, but you can see that at this point over here, when the animation starts all over again, you can see that the wave returns back inverted. But as it returns back inverted, the sine wave is still moving towards the right. So you have this inverted wave interacting with this upright wave, and as a result, you see this as a mathematical outcome. And that's what a standing wave is. Okay, so this sine wave reaching a node, inverting when it returns back, but now you're seeing the mathematical sum of the two, which creates this stationary looking vibration. That's a standing wave. Okay, next part. The different types of standing waves that exist. Okay, a good example for this, and I'll bring out my guitar, is what happens with strings. With strings, we have two fixed ends. With the fixed end, it's like a wave that reaches a brick wall. It's going to cause the wave to reflect and return back inverted. Okay, so you can start off with your lab. If you recall from doing this from yesterday, the first lab was to make it vibrate as slowly as possible so it looks like a skipping rope configuration, like so. So anytime a string vibrates like this is known as the first harmonic, or the fundamental frequency. And if you're wondering how in the world do you copy that in your notes, this is what you would do. Okay, you'd first write down your first harmonic, also known as the fundamental frequency. And you would draw these two solid rigid walls with a dot, a solid dot, to tell the reader that, hey, these two are fixed ends. Okay, you have your initial transmitted wave, and then after that, you got your reflection, and you'll draw it as a dot. So that's how you would note this in your notebook, okay? And that's what happens at a first harmonic. You'll notice that with your lab simulation, you could end up making it look something crazy like this. But you had to try really hard to make that happen, right? Because if you went too quickly, you wouldn't see it. You go too slowly, you wouldn't see it either, all right? You have to time it just perfectly. And if you time it just right, you'll end up having the illusion of a standing wave resonating at its second harmonic, also known as its first overtone. Now, when you write this down in your notes, you're going to start off with, again, your two solid boundaries. You'll start off with this S that looks like this, and you'll draw a backwards S the other way around. And that's how you denote the second harmonic in your notes. You can imagine what will happen at the third harmonic. Okay, unfortunately, I need to erase my notes over here, but I hope you get the idea of how to draw these pictures, right? By the third harmonic, as you've predicted, I'm just going to make sure that I line it up properly. Just keep the distances the same. And this time around, you're going to end up drawing your first incident wave like this, and then your reflected wave like that. And then you'll label it as your third harmonic or your second overtone. All right. And I need to erase all my notes now, just so that you can see the resulting wave, and it'll look like that. Again, these waves are assuming that you have solid dots on the ends. All right. So you're experiencing a fixed reflection. Again, when you were doing the lab, you'll notice that these waves, they only happen if you time it just perfectly. All right. If you mistime it, then it won't work out really well. And all this stuff here, I could simulate it for you real time using good old this, my favorite guitar. There's a hole in the bottom, so that's why, yeah, it's known as the holy guitar, because there's a hole there. It's a 20-year-old hole now. Okay, so let's go off and simulate all these things over here. Okay, I'll explain one more time afterwards. Or maybe this will help you understand what's going on. Okay, let's let a string resonate at its first harmonic. In other words, I want to make sure that both ends are fixed, and in the middle, it's able to vibrate. So you'll take your guitar and pluck it right at the middle, and the note will sound like this. I think I plucked it too hard. It should sound a lot softer. There you go. So it should sound like that. Okay. Now, if I want a guitar to resonate at its second harmonic, what I need to do is I need to pull one string down 1/4 of the way down over there, and I need to pull it up 1/4 of the way up here and release them simultaneously, all right, without skipping out even a fraction of a second. You'll see that it's not humanly possible, all right? You can't simulate the second harmonic that way. But if you've ever played the guitar before, you might know how to hack it and make it happen. If you take a look at the second harmonic, you'll notice that it forms a node right at the center. So this is what I'm going to do. I'm going to find out where the exact center of the guitar is, place my finger very lightly over there, and then pull on one end. When I let go of it, I'm going to keep this finger here because it's going to force the string to form a node there, and it will resonate exactly the same as at the second harmonic. So just as a reference, this is our fundamental frequency, and this is our first overtone. And if you hear it, it's gone 1 octave up. It's actually vibrating twice as fast. So we're comparing this with this. Oh, that's a better one. That sounds better. Okay, and you'll notice I'm not touching the string anymore. All right, so if you had a high-speed, high-resolution camera, you'll notice that the string is vibrating exactly the same as the second harmonic. It's doing this weird wobbly thing that looks like this. All right, where at the exact middle, it appears not to be moving at all. Now the wave is moving, but as we said, it's a superposition of the incident wave and the reflected wave. At that midpoint of the guitar, it's suddenly stationary. Okay, so how do you draw the third one again? One more time. What you'll start off with is that you'll draw something that looks like this. And then you'll flip it and draw it the opposite way around. That's how you draw it. Okay, you'll notice that on the third harmonic, you're forming even more nodes in between. So if I want a string to vibrate like this, then yes, I need to grab it right at the center of the string. I need to grab it at 1/6 of the way down, pluck them out of phase with each other, let go of them simultaneously, and make that happen. Again, that's even more challenging than the second harmonic. So since I can't naturally do that, you do a cheat. You take the entire length of the guitar and you split it up 3 ways, which coincidentally lines up at the 7th fret if you play the guitar. So you carefully place your finger right at the 7th fret and you pluck away over here, and I'll give you the reference note of the fundamental frequency, and I'll let you hear the third harmonic. Fundamental, third harmonic, also known as the second overtone. And it doesn't stop there. If you want to keep on going at it, you could generate the fourth harmonic as well. All right, so you can go and draw the fourth harmonic on your own. That's one of your homework questions. All right, but this time around at the fourth harmonic, when you draw it out, you'll notice that a node forms 1/4 of the way down the string. So in other words, you take the entire string, you cut it in half, and you cut it in half again. Coincidentally, that lines up where the 5th fret is on the guitar. So there is some math behind the design of a guitar. Okay, so you carefully place your finger right over here, and you can pluck wherever you want. In fact, you can even pluck over here. And now the string is vibrating at 4 times its fundamental frequency. All right, and you might have learned that already that, again, when you vibrate twice as fast, you go up 1 octave. So I start from that low E to the middle E. And if I place my finger right over here, I go from middle E to 1 E higher up, because now I'm doubling the previous frequency. I'm going at 4 times its fundamental frequency. Again, it sounds like this, which is exactly the same way how this note is pitched as well. Okay, so some guitarists, when you don't have a guitar tuner handy, that's how you tune your guitar using harmonics. That's at least one technique. Now you know. Okay, this is a reminder of definitions. What is a node? A node is a point in the standing wave where it doesn't seem to be moving at all. All right, so it's a point that remains at rest. That's what a node is. Some textbooks call it a nodal point. And the region which vibrates most violently up and down, this is the opposite of a node. And as we described from yesterday, it's called an antinode, or antinode if you want to call it that way. Okay, and you'll find out that mathematically it's always between 2 nodes. Lastly, this is the last trend. Okay, you'll see that between 2 nodes, you don't have a full wavelength. You only get half of a full wavelength. Right? If you want a full wavelength, like this whole sine wave over here, you need to go and count, skip a node and count Okay, so you have to double that distance. So that's a property that we observe. The distance between nodes is always going to be half of the full wavelength. Okay, so in that lesson that I talked about yesterday, I mentioned that I was giving you too much information in the example, and that's the reason why. If you have a tension stringed instrument, you don't need to know both numbers. All you need to know is either the length of the string or the wavelength, because the length of the string will always be half of the wavelength. I'll leave this up here for a moment for those to jot it down, and then I'll move on to the next slide. Anyone else need a bit more time? Okay. Just going to quickly restart this. I can see there's a rendering error with the text. That can only be resolved by restarting it. There you go. Now the text is cleaned up. Happens every now and then. Still glitchy. Oh well, I'll let it be. All right, just let me know when you're done copying it down. I see 2 hands up. That's fine. Okay, so one last thing I want to talk about before I move on to the next slide is just watch out for the labeling. I think this is where most students hiccup at these definitions over here. You'll notice that the third harmonic is not the third overtone. Okay, so there's a misalignment in these numbering systems. The first harmonic is known as a fundamental frequency. Okay, so there's no other name for it. It's just a fundamental frequency. And then when you reach the second harmonic, because it's not the fundamental frequency anymore, now you're at the first overtone. So that's what I wanted to point out. Okay, just watch out for the labeling that the numbers are slightly off from each other. The third harmonic is the second overtone. The fourth harmonic is the third overtone. The fifth harmonic is the fourth overtone. Okay, so just watch out for the numbering. They are off slightly by 1. Okay, next example. I think we have two math examples, and then we're done for today. Trying to fix it up because that's just weird how it's rendering it. Okay, I guess I cannot fix that until I restart PowerPoint, so I'm just gonna go with the flow. So this is a story about, just a happy gentleman who's trying to feed a little duck, and the duck is so excited that it bobs up and down. And coincidentally, when it bobs up and down, just by the dimensions of the river or the pond itself, it results in this illusion of a standing wave. All right. So, and this is what the person who was feeding the duck noticed, that the distances between successive nodes worked out to 38 centimeters. All right, so the distance between nodes is 30 centimeters. And if you recall from before, as I mentioned, that does not represent a full wavelength. That is only half a wavelength. So if I want the real full wavelength, I'm going to take that number and I'm going to double it. That's the logic behind it. Okay, and that's why the formula looks something like this. dn is equal to half lambda, and some textbooks will show a letter N in here. Others will just simply drop it. Just to remind you that the distance between a successive pair of nodes, okay, so not the 0th node, but the one after it, is going to be equal to half a wavelength. So intuitively, if you know that that only represents half a wavelength, then a full wavelength is double of 38, or 76. Okay, so yeah, you can probably solve the answer in your head, but I just want to show you that you can also solve this mathematically as well. So if we're trying to solve for the wavelength itself, then first thing we need to do is we need to double both sides by 2. So we get 2 dn is equal to lambda. Okay, and then when we flip it around, we get lambda is equal to 2 dn, or d1 for the first nodal pair. Okay, so 2 times 38, it'll give you the same answer. 76 centimeters, which you probably want to convert into meters, not because it's the final answer, but it's because what you're going to use with it next. The question is asking about the frequency of the duck. Okay, and we know that if we know that v equals f lambda, which we covered this a few classes ago, then f is equal to v divided by lambda. And again, the only way for this formula to work out properly is if lambda was set to meters. And that's why I quickly converted it to meters. So beyond here, we have the information to solve this problem. V is equal to 0.95 meters per second, and lambda is equal to 0.76 meters. So 0.95 divided by 0.76 gives you 1.25. And there you have it. Okay, so the frequency of the duck is 1.25 hertz. If you give me the answer of 1.3, I'm totally fine with it. Okay. Technically speaking, it should be 1.2 because of the rounding rule, but we'll skip out on that for this course. Okay. So whether if you give me 1.2 or 1.3 on a test, I'll accept both of them as correct. Down below, I'm giving you a heads up on the next example. So I'm just going to give you guys a bit of time to start jotting it. And don't worry, example number 3, I'm going to bring it all the way up to the top afterwards. Can I bring example 3 up to the top now? I hope you guys are done with example number 2. I'm just going to bring the text of example 3 to the top. Okay, and along with it, just a picture in case if you need a picture to understand what's going on with it. When it comes to test time, I'm probably just going to give you just the verbal words, and then you'll have to briefly sketch it out mentally so that you know what the question's asking. Okay, so in this question here, it's a standing wave, and we notice that it's a total distance of 45 centimeters between 4 consecutive nodes. All right, so there are 4 nodes that are drawn, and there are 3 antinodes that you'll observe here as well. You'll see that there are 3 antinodes. All right, so first question is, what is the wavelength? And number 2, what is the corresponding frequency in the setup? With this drawing over here, some of us can figure out the answer intuitively. If it's 45 centimeters from end to end, and we cut it up 3 ways, that means that each one of these are 15, because 15 plus 15 plus 15 gives you 45. And as you may know, a full wavelength is going to be double of that 15. So there's your answer. That's the wavelength of the wave. All right. But if you needed to prove this mathematically, then here is the proper process behind it. What you'll be doing is that you'll be counting the number of antinodes, and the antinodes will be your value of n for your dn formula. Okay. So this one you can consider it as the 0th node. The next one beside it will be the first node, the one after it will be the second node, and the one after it will be the third node, or you can just simply count the number of antinodes. Either way will get you the idea that you're talking about D3. Okay, so when you go back to this formula over here of dn is equal to 1/2 lambda, you're going to multiply that 1/2 by 3 times. So D3 is going to be equal to 3/2 lambda. Or if you carefully rearrange this, then lambda is equal to 2/3 of D3. So lambda is going to be equal to 2/3 of 45 centimeters, and that will also give you 30 centimeters, or 0.30 meters. Lastly, because the givens also give you the frequency is 30 hertz, you can now find out the corresponding speed, because v is equal to f lambda. So speed is equal to the frequency of 30 hertz, or 30 per second, multiplied by 0.30 meters, and that's why your final answer will be measured in meters per second. This is all PowerPoint animated out, so there you go. There's the cleaned up version of the same problem. Now, n, it depends on how you want to count it. Okay, students asking, well, what should you treat n as? I'd say that it makes more sense to count n as a number of antinodes because it just logically makes more sense, right? Because when you have one node, do you have a wave? Right, you need to have at least 2 nodes for that standing wave to exist. So that's why I said that logically speaking, this n over here is n is equal to 0. Okay, for your 0th one. So really, to the distance between 2 consecutive nodes, then you have n is equal to 1. And then this one in your mind would be n is equal to 2, and this one will be n is equal to 3. And that's where the 3 comes from. Okay, but another way to count it, which is perfectly correct because it will give you the same exact answer, and it's probably less confusing, is just to look at the number of antinodes. It will give you the same answer as well. Because the first antinode generated, then that will be D1. Okay, so I hope that that clarifies that. D is for the distance, right? It's the distance between those nodes. Hope that answers your question. Any other questions, guys? Okay, if there aren't any other questions, then that is it for today's lesson, at least on what you need to know. All right, course back page 65, questions 1 through 5. And once again, thank you guys for joining me. I'll catch you guys in the next episode. Bye now.